Okay, you see the slide, is it okay?
Yes, sir, it is visible.
Yeah, okay, it's good. Okay, good afternoon, ladies and gentlemen. I would like to continue, and this is the main topic today is hazards affecting large dam projects. And you will see we will have really a large number of hazards which have to be considered, which is quite different from, I would say, building structure, bridges, or other infrastructure projects. So if we look into the hazards and the design criteria, we have to distinguish different types of hazards. On one hand, we have hazards from a natural environment, we have man-made hazards, and we have site-specific and project-specific hazards. So we can group them, and there is some overlap here between site-specific and project-specific with some natural hazards. And if we have different hazards, please keep in mind that to design against hazards is one of the options, and for that purpose, design criteria have to be specified. There are, however, other options, basically to eliminate hazards, to accept hazards with low probability of occurrence, like meteoritic impact, we can say, or to control or monitor hazards by appropriate monitoring systems and emergency planning. Okay, to eliminate hazards, how can we eliminate hazards? If we have a powerhouse, if you have a surface powerhouse, for example, which may be subjected to rockfall, we can build an underground powerhouse when rockfall hazard has been eliminated. So there are different options how we can deal with hazards. As I've said, we can design for that against these hazards, but we can also take other options, and to design against hazards is not always, of course, the most economical way to deal with hazards if there are other alternatives. So we should never forget about that. I have shown this hazard matrix already in the morning, and I would just like to repeat here once more. We have the hazards on one side, and we have a protective measures, and the protective measures go from rehabilitation, partial reservoir drawdown, because we, let me say, for the safety of the people living downstream of a dam, let me say, the danger, if I may call it like that, from a dam project is actually the reservoir, is the water in the reservoir. If you release it in a catastrophic way, it causes a lot of loss of lives and so on. We can have a full reservoir drawdown, we can have an evacuation. I would always say typhoon and so on, hurricanes. Basically, we have some warning times of 3-4 days. So we can do some evacuation, but in the case of earthquake, I mentioned the warning systems which exist, I must say, are only a few seconds, 10 seconds, so we cannot evacuate people, so we can only do post-evacuation, and once a dam has failed, and we can do the, let me say, still some evacuation of because it takes some time until a flood wave propagates to some places. But from these hazards, I would like to draw once more your attention. Earthquakes are unpredictable, so we have to assume that it causes some damage if it is destructive. And the same unpredictability is if you have sabotage, terrorism, or some criminal action, or some acts of war, so you can only work on post-evacuation, post-event evacuation, and therefore these two hazards in in the overall safety of projects are, I must say, the most critical ones. I would say they are very rare hazards here, but if you look today, for example, in nuclear plants and but also in dams, the earthquake hazard has become one of the most dominant hazards, together with the flood hazard, if you look from a natural environment. But flood hazard is a simpler one, if I may call it like that, than the earthquake hazard. Okay, but this is brief repetition. Now, I would like to give a discussion of the different types of hazards. We look first in the natural hazards, in dam projects, and the protective measures. The main natural hazards are floods, earthquakes, mass movements, landslides, rockfalls, avalanches, and we can say extreme weather conditions, storm, rainfall, low temperatures, ice, and so on. So these are the basic hazards from the natural environment. And to deal with these hazards, basically, we can deal, if we have time, we can do a rehabilitation. We can also do some rehabilitation in earthquakes, of course. We can do partial reservoir drawdown, as I've mentioned, for mass movements. If somebody sees a risk of a mass movement into a reservoir, we can lower the reservoir there. And afterwards, in the case of floods, as I mentioned with floods, we have some extreme weather conditions, so we can do some evacuations. In the earthquake, basically, we cannot do the prediction. So this is a kind of an overview. Of course, there are some, let me say, cases in between which are also possible to some extent for different projects. So this is just a kind of a guideline. This is not an absolute scheme, but it shows you what kind of measures are most likely applicable to these different types of natural hazards. Now, I've also shown this. This is a picture from Switzerland from the late 70s. This is a arch gravity dam with a free flow spillway. It is also near the Italian border here, a few hundred meters up is Italy, and it was an extreme rainfall, and it has washed a lot of floating debris in the reservoir, and this floating debris, as you can see, has blocked the free flow spillway, because usually free flow spillway, you assume they are absolutely safe if the water would be clean. But here, I would say the deficiency is that the spacing of these piers, spillway piers, there is a bridge across this spillway, is too narrow. So this floating debris, it blocked the spillway and it overtopped the dam, and you can see the abutment. There are some parts with loose material here. It's washed away here on the right, and also on the left abutment we have some erosion taking place. But the characteristic of our, let me say, floods is that the catchment areas are relatively small, so the floods are of short duration. They have a high intensity peak, but they don't last for hours, they last for a relatively short period of time. So this based on this incident, until that time, basically for the spillway design, it was assumed that the water is clean, no floating debris. Basically all spillways had to be reviewed in Switzerland, and they have been upgraded within the next, within a period of about 20 years. It is not just done from one year to the other. Usually it takes quite some time. We see here another case. This is from 2015, is in Myanmar. This was a newly built dam, and it was Sakhain province. It's not far from India actually. So during an extreme rainfall, a lot of debris was washed into the reservoir, and you can see here it is also a free flow reservoir, which would be absolutely safe if the water would be clean. But as you can see here, the debris piled up quite a bit, and not much water here is being released. Basically, this floating debris blocked with spillway. Maybe the openings were about 8-9 meters, which is not enough. In some places, like in Switzerland, we think the standard lock length is 10 or 12 meters, but this is in some places this is a very optimistic assumption. You know, if you are in some tropical areas, you have a much bigger trees, and 10, 12 meters may not be adequate. Okay, so that is this case in Myanmar. You see here it is an embankment dam. This is Spillway, and the dam was just more or less completed. You see here the reservoir is basically full of floating debris, and because the contractor had not yet left the dam site, therefore this equipment was still here, some backhoes. So they were placed here. It was a kind of fortunate, I must say, and they removed here some of the floating debris, and allowed some greater, we see here, release of water from this spillway. But you see here, it's it is maybe 8-9 meters of spacing. It's not enough. But you see here, these trees, they basically blocked the water almost 100%. Very little here, a little more comes, but it really blocks this spillway. Okay, afterwards, downstream, they used. I liked this photo here because okay, you have elephants in India, but we do not have elephants. Okay, for us, it's an interesting photo here with elephants helping to clear the floating debris in the downstream parts. Okay, there are plenty of locks there in that area. And we see here, this is a dam, it's an embankment dam. And we know embankment dams are vulnerable to overtopping. And because this spillway, a free flow spillway, which I say is really the best way, the best spillway in terms of safety, if it is properly designed. So because of this floating trees, they blocked the spillway, so the water level was increasing. And if they would not have been able to mobilize this backhoe, you know, what I've shown here, if they would not have been able to mobilize that, I would say the dam here it was a new dam. You can see here, it was just inaugurated. It would have been overtopped, and if it would have been overtopped, it was close to failure of this new embankment dam. This is just about 6 years ago. Okay, so floating debris is really a problem. They have also, it is about at the same time, if the capacity of the spillway was not enough, they had some other dam, as you can see here, at the crest, still over parapet wall. They had experienced some dam overtopping of some other dams. And of course, if you have a longer term overtopping, it eventually will erode the dam body or embankment dams. So there was this extreme rainfall in July 2015, and we see here after the earthquake, we have here this parapet wall which I mentioned. There is the, after this event, downstream phase, quite some erosion. Just a few days ago, there was also overtopping of a dam, Embankment Dam in Brazil, where due to a landslide, not due to rainfall, due to a landslide in the reservoir, impulse wave was created, which overtopped the dam. The reservoir was small, therefore the landslide displaced quite a bit of water, and then water was overtopping the dam crest during a longer period of time, not just a few seconds, as in the case of a wave, it overtopped them during minutes. Okay, this is the same case I've shown previously in Myanmar. Okay, and another issue is, of course, if you have landslides, like here, this is from a Wenchuan earthquake. I have shown it one. Pointer doesn't want to come. Okay, here we see this landslide here at the right abutment, and due to the earthquake, here's the intake structure for the power waterways. Here, the power plant is a few kilometers downstream. This is the intake structure for this head race tunnel. So, due to the earthquake, the power failed, and the emergency power supply also somehow was not working. So therefore, it was not possible to open the gates. It is then clear that hours or even days, depending on the size of the reservoir, if the water is still continuing here flowing into this small reservoir of this Ramos River power plant, you have this overtopping, as we can see here. So we will have overtopping. It is different from the overtopping I've shown before of embankment dams, which can be eroded. Here, the overtopping basically is not a big problem. Well, it is still a problem, but not a serious problem like an embankment dam, as overtopping of concrete dam is not that critical. Of course, it depends on the amount of overtopping. If you have only overtopping of, let me say, 20 centimeters, 50 centimeters, it has no effect on the safety of a gravity structure like here. But in case you have, let me say, overtopping of 4 meters of 10 meters high, or let me say 50 meters high gravity dam, then 4 extra meters will probably increase total water load on that dam very substantially, and the sliding stability may no longer be okay. So therefore, if you have high overtopping of such a gravity structure, you may end up at the sliding stability problem. So sometimes people forget that. Also, the overtopping does not create erosion problems like in the embankment dam, but it may create a sliding stability problem. What can we see here for the dam, which I have shown before? What is the result of overtopping? Okay, if we have extreme floods, carries out, it brings along a lot of mud, and after overtopping, you have to clean up this dam. And of course, if you have equipment on the dam crest, it may be damaged as well. We see here another case. This is in Laos, is at Sayaburi, is at the Mekong River, and in December 2013, there was a flood in the Mekong River in December in a dry season. It was a so-called dry season flood, where the water level in the Mekong increased a few meters. And at that time, the coffer dam here protect the dam site, which was under construction, which was also modified. And in the, let me say, in the dry season, it was assumed the water level to be low. When it overtopped this coffer dam and it flooded the construction site, yeah, it's about 20 meters of water. And you see, of course, if it brings in the muddy water. So therefore, a lot of cleaning and pumping work had to be done, and it was basically possible to do that in a reasonable time of period. In some places, people thought it would delay the project by many months, but it could be cleaned up quite quickly. And as this failure here was a kind of a progressive erosion here, so people who were working here had time to evacuate and also to transport away some heavy equipment. Not everything got lost. So this is just a kind of the end situation. And here we see some towers which were used as parts of the conveyor belts for concreting these large hydropower run-of-river power project, which is in operation now. Okay, this here is a picture in Pakistan. It is in the Neelum Valley. It's a tributary of the Neelum River in Kashmir. And you see, it was, I think, in 2011. It transported a lot of sediments here, of course, sediments. And you see here, there was a weir here. The weir, the two gates, and here is a free flow. It is all covered with large boulders. And there was a switch yard here, a little downstream, also very close to the riverbed. It was completely washed away. And also even here, these, let me say, these gates, these are already new gates. The gates were also severely damaged and had to be replaced. It is not critical, that critical as the case you have in India, in the Chamoli in February, where actually, let me say, real floodway caused a huge construction. But here, you know it very well, in the Himalayas, you have a lot of sediment transport, which has to be taken into account. This is again a photo from a project in Laos. This is the Namtön 1 from last August. And as you see, this is a RCC dam here. And in this RCC dam, there was also a heavy flood. It reached this level and it exceeded the diversion flood and it overtopped the dam, as you can see here. Okay, just before somebody asked me about joints in gravity dam. This is a RCC dam, I must say, and maybe you can see here in this case, people have provided shear keys, okay, to limit relative movements. Basically, the shear keys you would provide to limit relative displacements between blocks due to seismic action. So there are these shear keys along these block joints. So this is in Laos. But I must say it was planned already in the design that if the diversion flood will be exceeded and the, let me say, construction is already progressing, it would be accepted if the dam, because this part is left open intentionally here during the rainy season. that it could be overtopped, and we see here we have overtopping of a few centimeters. It's not critical. Here it looks a little more critical. It is a Tekesi arch dam in Ethiopia. It is located in this problem province in Tigray. Okay, this is the highest arch dam in Africa, about 186 meter high. And you see here during, this is a tributary to the Nile River, and you can see here during construction also they left some openings at the lower level in the case of larger floods exceeding the diversion floods. So the construction site here with two blocks were overtopped, as we can see here. So the flood hazard is quite some hazard. Also, with respect to erosion, I would give this photo from New Zealand in 2016. There was a very strong earthquake, which caused about 100,000 rock falls and landslides. A very huge number. Here is a photo of a landslide which blocked the river here, and it formed a landslide dam. And we can see here there is some seepage through this landslide dam, and then eventually it would be eroded. Okay. Now, further on with some floods, I must say in Europe you have quite a few examples, and especially in Italy, we used to do a field trip every year with some friends, with some study friends. We go to visit some sites of dams which have failed in Italy, because there are more of them than elsewhere, or the remnants of a failure can still be seen in Italy, whereas in other places they would be removed. Okay, anyway, this is a dam, Cervino Masonry Gravity Dam, we see here. Okay, this is a saddle dam, it's a side dam. It's not the main dam. And in 1935, there was also a flood, and the spillway was only provided on the main dam. So the spillway capacity of the main dam was not sufficient. So this dam was overtopped. And as I said, if the dam is not very high, if it is overtopped, you may end up in some stability problems. So you can see we visited this dam. It was even hard to find it. And you see here, this is the abutment. This is the right abutment of the dam, which I've just shown here. Okay, let's see, this is the part here. So the road was on the other side when we were traveling there. So you see some serpentine material. The rock was a little questionable, but you see here this masonry gravity dam. It was completely washed away. You could not see anything. It has gone completely. Okay, so due to a flood in 1935. So it is not just overtopping of gravity dams, which is no risk, let me say. But if the dams are not high and you have a substantial overtopping, and if there is, like in this case, also some problems with the abutment, it can be completely washed away, as is the Cervino Dam. So therefore, it is a good example. This photo I've shown already. Okay, I've been involved for several years in Latvia, former Soviet Union, and where in spring, in winter, the river is covered by ice, and in spring usually we have a big floods here, and this just shows once more opening of this opening here. The gate has been removed, but here in the others, they are just in the process of lifting. Here, you see it already lifted partially. This also, so water is coming beneath this gate. Okay, so that is the problem. Is here, I must say that as I've discussed before, that you may not be able to remove all these gates if a flood is coming. Of course, the floods in this area is a large catchment. These are not big waves which arrive in a few minutes. It takes hours, and people know when the floods are arriving. So people have some time here. But it shows if you have the gated spillways, and if you cannot open the gate, it can have large consequences. If you have ungated spillways, basically your dam is safe from floods if the capacity is enough. Okay. So this is again ungated spillways from Myanmar again. Okay, what I want to show is here water is splashing up quite a lot, and I think it is not really the maximum flood. So probably in the design, people have underestimated the sidewalls. As we can see, the height of this sidewall is not enough. This is another picture, and of course, this sidewalls could create some safety problems as well. And we have also seen from the Oroville Dam that there are some spillways which have some structural safety and which have some hydraulic safety. Here in Myanmar, I've seen some other spillways. My impression was it would have been better also in some cases to do some hydraulic model tests to improve basically the flood safety release. Okay, that is with the flood as a first hazard, and it is clear for each dam project. I must say the most frequent hazard and the hazard each dam has to be able to withstand is a flood hazard. Floods basically occur every year. Now let me look into landslides and rockfalls. Okay, you had this problem in India in February, but this is not a new problem. You see here, this is in Peru, is a Mount Huascaran. They also have high mountains. It is almost 7,000 meters high. So there was also a nice rock avalanche, which fell down here during an earthquake about 3,000 meters and propagated through the valley here and caused the loss of life of many people. You see, this is a photo taken before the earthquake, and I just want to show the photo after the earthquake. It was in the 1970s or 50 years ago. So it killed here. So this ice fall, it propagated here 20 or more kilometers through this valley. It destroyed this city, and it killed about 20,000 people. Now, this is, I would say, the most destructive one. There are no hydraulic structures, but I would say it has some similarity with your case in Chamoli, where you also have a nice drop, a quite substantial drop, and then the wave, I will show it, propagated along the valley at high velocity, but there were some hydropower plants. But I just want to say this is not new, but if such debris, which here was about 50 million cubic meters, of course, encounter some dams, with the smaller reservoirs, I must say to cope with 50 million cubic meter debris flow, you would need a reservoir of, I don't know, 200-300 million cubic meters in order somehow to account for such or to block the propagation of such debris flow. Okay, so this is the famous case in Peru. Now let me say come to the case in India. We have some similarity. This is in the early February, and this is a photo I've got from a presentation of Mr. Vishnoi from Terry, and he has marked here, let me say, the origin of this ice and rockfalls, which then propagated through this valley here, and along this valley there were some hydropower developments going on. You see here where it's, for example, it's Tapovan, Vishnugad barrage, and this is just a photo at the time of when this wave arrived. Of course, this wave is a catastrophic wave. It's not easy to stop such a wave by some big reservoir. It would still create big impulse waves if it would hit a reservoir. But you see here, this is basically a debris flow here with water mixed with some water, which destroyed this barrage here. And I think if you're here, if there is no warning system, you cannot survive here. See here some other parts of Tapovan Vishnugad hydroelectric plant, because there are some diversion structures, and you see here, I think one gate here was also washed away here from this incoming debris flow. This is the further downstream of this, let me say, ice and rockfall. This here is the same plant showing before it was under construction, and afterwards, basically all in the sediments here, all covered in the sediments. What can be another one? Rishiganga barrage, also just before hitting. You see here, this is a small structure, and when this, let me say, debris flow arrives, that it will basically destroy that. And this is after the event. We can see this structure, or concrete structure, massive structure, is also completely washed away. Okay, what are the lessons learned from this incident, and also what I've shown from Peru is the mass movements in the catchment area of the dam project must be included in the assessment of geohazards of dams. Of course, the same applies to this glacial lake outflows and the breach of landslide dams. Okay, usually people are not used even to look into the catchment area, but I must say the case here of India has shown that in some areas, like in Himalaya, you actually also have to look in debris flows which may be created in the catchment area, and not really even in the reservoir area of these dams. Now, the critical issue is that these mass movements, okay, we do not really know what are the trigger, but if the stability, or let me say the safety factor static safety factor is close to 1. It needs just some small trigger that such landslides or rock falls can be released. And one of these typical triggers would be earthquakes. So therefore, if a strong earthquakes occur, there is a great likelihood that you have in such areas you have many rock falls. Now, what is the lesson number 3 is dams with small storage which cannot absorb the volume of debris flows actually should not be built in such regions. This applies in particular to run-of-river power plants with small storage volume. Yeah, we know run-of-river power plants in steep valleys, they have, even in Switzerland, along the main river, the reservoirs are only a few million cubic meters. And if you have a debris flow of 10 or more million cubic meters, you cannot stop a debris flow by such a small reservoir, and basically the dams will be washed away. And I must say, if you have this hazard, I must say you could if you think physically about that, you could only build dams with large reservoirs. If you buy small dams with small reservoirs, yeah, they are unsafe, and they should not be built in such areas because there is nothing you can do against that. It is very unfortunate. Okay, now what is the biggest dam which exists? The biggest dam in the world is this one, is a Usoi landslide dam. It's about 2.5 billion cubic meters. Okay, so it is in Tajikistan, in Pamir Mountains, and it was created under 10 years ago by a magnitude 7.3 earthquake. And the height of this dam, of course, we see here the crest is something very irregular. The height of this dam is about 650 meters, 600 or 650, it depends what is the reference you take here. It's the biggest dam in the world. Is a landslide dam. It's a natural dam, and it still stands very for it creates a big lake, which is called Lake Saras, and there is some seepage through its dam body, but I think the dam has already settled since 1911. Somebody mentioned about 90 meters. Some parts also consist of ice, which melted, so it settled 90 meters is a lot. So there is some seepage and there is some, let me say, some erosion further downstream, but it is very thick, the dam, so it is still there after more than 100 years. This is the biggest landslide dam, which was formed by the Wenchuan earthquake in China in 2008. And here, this is just upstream of what we call Beichuan village. I visited that. It was destroyed here. It's about maybe 2 kilometers away from here. Many people were killed there due to landslide, but just upstream of this town, there was this landslide here, and it blocked this Minchang or Ming River and formed a reservoir of, I thought it was about 200 million cubic meters. The water level was just increasing. So people were very much concerned, because if it would breach this dam, it may flood. This is near Chengdu. It may threaten about 1 million people, a lot. Okay, so therefore, you see here some roads. The Chinese brought in some equipment, the army with the biggest helicopters, I think some Russian helicopters which were available, transported here some construction material, and they started constructing a channel here, and this shows, of course, this channel, once water is flowing through the channel, it is eroding progressively, and this is during the course of this channel, which I cannot say how big it is, but let me say maybe 50 meters wide or something like that. But here, with a progressive erosion, of course, it washed everything away, and the flood which then was created corresponded, as reported, to a flood with a return period of about 250 years. You know, for big dams, you consider 10,000 years. So the flood which was released, 250 years flood, which I will say is a great success, because if there would be sudden erosion here of the whole dam, it would create a flood maybe with 10,000 years flood. But still, this you can see is a lot of debris here, and in this city, a little down there, still a few people were killed. Also, this was done only, let me say, maybe 2 weeks after the earthquake. Some people who have not been evacuated were still killed, stayed near this river. But this place was absolutely inaccessible, and people even didn't know it. Most people were living downstream. Okay. Okay. Well, the typical hazard which we have everywhere, and I think when I see some photos or YouTube movies on rock slides, there are interesting videos, I must say, from India, okay, from the Himalayas, in Himachal, in Kashmir, where you have spectacular photos of rock falls in your steep mountains, but we also have that in Switzerland. You see here is a block coming here down to this road, so granite block, and in Switzerland, we say we are keen. We want to have forests everywhere. So therefore, in areas which are prone to avalanches or some rock falls, we, as a first protection, we provide forests. Forest is a protection basically against avalanches. But of course, when you have this kind of big boulders here, 100 cubic meters or so, this forest is not able to block that. But it may cause some problem. So we have, let me say, tens or hundreds of kilometers of nets already, which can absorb quite some boulders. We see here quite a big boulder which was caught by this net, but we see here the steel post here is already deformed. Of course, it has to be replaced completely. Okay, how further much it would have been moved, okay, we also don't know. But this is close to a railway, so it is quite critical. This is another one in Iran. It actually just happened when I was there, just 2 hours. So there was somebody building an access road to the dam, and the rock was quite weak. And this person here in a backhoe did some work, and this you see this block moved up and killed that people there. It's quite depending on on the geology and on the condition of the rock here, you can have this kind of accidents occurring. This is not new to you. Okay, we have a rock slide. This is the same project I've shown now just before in Iran. This is a rock slide due to impounding of the dam during filling of a reservoir. You see here, this is relatively close, so a part of a rock basically is moving. I must say before impounding, a geologist did make a survey of potential areas which could slide into the reservoir, but okay, usually this difficult. He has not predicted this one. Okay, this usually may occur even somewhere else, but we have made some assessment, but it was not, this is an uncritical one. You see it just moved down here, maybe less than 10 meters, so it did not create, it moved down slowly, so it doesn't create a wave in the reservoir. So it's not a problem, but it just shows that due to the filling of the reservoir, you can destabilize parts of your rock formations along the reservoir rim. There's another case here, a bigger one. It is the same project. You see here, there is a bigger landslide here, which also developed, but it was also not, or which is a potential. Did not really move here, but it was considered as a critical slope. Okay, the most critical here was basically here. Which had a volume of about 2.5 million cubic meters, which also started, we see here the scarp, which started to move down here, but the movement was a slow movement. So it is not a problem of it was not really a problem of the impulse wave, but it is more a problem that if the debris here flows into the reservoir, it takes up some volume of the reservoir, because the reservoir here was about 250 million cubic meters. Okay, what is critical now if you look into arch dams? I've shown some of the blocks. This is the arch dam, which for many years was the highest arch dam in the world. And you see here at the left abutment, where here is some retaining wall, so unreinforced. There are some blocks falling. Actually, these blocks about 1 meter thick, or 1 meter 20. It's not very thick. So it destroyed this wall. Okay, here it could not stop it, and it damaged here. Let me say the railing at the dam crest. In addition, there are only a few blocks, but they come from quite high. And as you can see here, we have the impact of these blocks on the concrete of this arch dam. Okay, these are here. This is just a close-up of this impact craters here, these two. And you see here still some of these blocks. But I just want to say, if it's maybe 50 centimeters deep, but it was not critical for this dam, because the dam here was about 14 meters thick. It's not a problem, but there are dams which are built, arch dams, unfortunately, and also in Iran and in World War I, 3.5. It is only about 3.5 meters thick. So it would be quite different if such a block would hit the dam. If the crest thickness is only 2-3 meters, it would basically, it will destroy the dam. Well, locally, it will cause crack and everything, and it may even penetrate, as we have seen here. This retaining wall cannot stop this blocks here. I must say it is not a reinforced concrete. It's here just a plain concrete wall. Okay, what is the rock falls? This hazard, I must say, the number of rock falls is a big problem. This is also from a Wenchuan earthquake. This is a road, access road to a big dam, I think 132 meters high, Chapai Arch Dam. And it was basically not possible for almost a year to access the dam site, because the road looked like that, and people had to go there hiking. But it was not possible. It is quite important that if a dam should be damaged, that you can bring in equipment and so on to rehabilitate the dam. But in some areas, the access roads are blocked, as shown here. You have additional problems. I would also like to mention that in eventual earthquake, there are, okay, it's difficult to count the number of rock slides, but some people claimed there were 200,000 rock slides, rock falls, caused by this eventual earthquake. You know, a huge number, and I must say these rock falls can have various impacts on dam projects, and basically they are not really looked at as others. Okay, in the mountains, this is from Austria, you have avalanches. This is, what shall I say, powder snow avalanche. I may call it like that, or we call it like that. If the temperature is low, the snow is basically powder snow, and we have this impact of this avalanche on a dam in Austria, and okay, just it's beside, but I would say these avalanches, this is a powder snow, if I may call it like that here. It has no effect on the dam, you know, but it looks very spectacular. So you could have that, but if this would be a rock fall mixed with rocks and so, it would be a big problem. Okay, the other one is cold weather. Cold weather, I think you do not have too many places with cold weather. Only in the Himalayas. But here is in Latvia, the project I've shown this morning. Yeah, during this time of the year, they have, I was there also, we had minus 20, 21 degrees, but this is an old photo which just shows the formation of the ice at some electrical substation near the dam site. Okay, now let me say a few words. These were, let me say, rock falls and some temperature. Let me say a few words about seismic hazards affecting large dam projects. I've shown already a few, and I would still show this slide a couple of times. I hope you are not too worried about that, but it is important when people underestimate or ignore the fact that the seismic hazard is not only ground shaking, as specified in seismic design guidelines. We can have a fault movement. I've discussed it already. At the dam site is very dangerous for concrete dam. Fault movement in a reservoir can trigger landslides or some impulse waves. And we have a mud movement or rock falls or landslides causing all kinds of damage, because the numbers are extremely large, especially in mountainous regions. And there are some other hazard site-specific, project-specific. I would say liquefaction is, for example, a site-specific or a project-specific, depending on the type of dams, or we may have some foundation movements and so on. Dams on faults, I've mentioned already. This is in Iran. We have plenty of faults. We have plenty of tectonic movements, like in the Himalayas, the Zagros Mountain, just showing this continuity. Actually, which is not a, this is a secondary fault here. Just this is the basically at the location of a dam axis, which originally was planned to be an RCC dam, and based on a reassessment of faults here, the dam type had to be changed, because the concrete dams are very vulnerable to fault movement. The dam would have been okay for ground shaking, but it would not have been safe for fault movement. So it has to be changed. You see here some faults, the nice surface. It moved here already a couple of meters, so it's basically polished here the surface of this fault. This is the other fault. This is the main boundary thrust. We see here, this is along the Neelam River in Pakistan, in Kashmir. And what you see here is, I have shown this already, this is the location of the fault. And the fault basically passes through the dam site. And the dam site is a concrete dam, and in a part of the main boundary thrust, which is a capable thrust, which is can have larger displacement, an embankment dam was built here across this fault zone of about 50 or so meters. Okay, now this is a picture I've taken in Ethiopia. I also didn't know that this exists until I was there. It happened just a few weeks before they showed me this. But this is in a rift valley in Africa, where basically continents is formed. So therefore, you have extensional cracks, as you see here. And these extensional cracks, yeah, it is about almost 10 meters wide, and they go quite deep. And it is quite obvious. It was new to me also. It is here about 900 meters long. We walked along this fissure. And it is clear, if you have a dam built at such a location, it is impossible. Also, whereas in the previous one, here where we have a trough, basically a trough, the material is still in contact. So you can build something. But if you have this situation, that suddenly a big fissure develops, and in Ethiopia, in this Rift Valley, they have quite a few of these. You can see some of canyons, which were now look like canyons, but originally they were fissures in the earth. And if you would have a dam which would be affected by something like that, I must say, barrier for sure, in my opinion, you cannot build any dam. Okay, so for me, was a new feature in that Rift Valley in the eastern part of Africa. Now, okay, for the Venge one, as I mentioned already, there is this epicentral region. There is a huge number of rockfalls. Basically, yeah, I don't know who is able to count them. But it is a big area, I think more than 1,000 square kilometers, which were affected by that. This is a picture taken from the crest of a concrete face rockfill dam. This is just a few hundred meters away from the dam, and it's a 152 meters high dam. But you can see these rockfalls occur very close to this dam, and they come into the reservoir. But at the time of the earthquake, when I took this photo, this was about almost 1 year after the Venge 1 earthquake, the reservoir was only 30% full, so the water level was very low. Therefore, when these slides, they are kind of, let me say, shallow slides. They did not create any dangerous impulse waves in the reservoir. But it just shows that this picture is a good example to show that during the earthquake, you may encounter some landslides very close to the dam site. Okay, which we have in Iran, also 30 years ago now, already is a second root dam, buttress dam. And in this buttress dam, okay, this earthquake, I will explain it then separately in detail. I just go through quickly. We have some big boulders here which fall down, and just below these boulders, we have here this railing. Is actually the intake of a spillway. Morning Glory Spillway. It's just above that. It's just fortunately these big boulders did not fall into that. Now in the Embankment Dam, this is the Tohoku earthquake, March 11, 2011, where this dam it was about 18.5 meters high. Due to ground shaking, it failed, and the reservoir was released. Okay, the failure mechanism is somehow a combination. You release some water. If you release some water, this is basically equivalent to rapid drawdown. And if you have rapid drawdown, you will have at the upstream phase some stability problem. So stability accelerated then the overall failure of the dam, and it caused stability failure along the reservoir rim. As we can see here, these are not earthquake. Well, in that sense, they are not earthquake cracks due to ground shaking. They are the result of a rapid drawdown due to the catastrophic release of a reservoir within a few minutes. So the rapid drawdown destabilized the reservoir rim, as you can see. Okay, these pictures I've shown already here from a Butch earthquake, also 30 years ago, 20 years ago, and we have large fissures which come from some stability failure. And as you can see here, I have shown that also before, we may have quite some substantial earth fissures if some parts here are separating and moving, for example, here in direction of the reservoir. Typically, the cracks in embankment dams often are along the dam crest, as shown here. I have also shown this. I like to show this photo because it also shows these plastic sheets. These plastic sheets have been provided to protect these cracks from infiltration of rainwater, because if rainfall, because this material here, I would say the conductivity would be, the permeability would be very small here of this material. So if you would have water coming in here, it would build up a water level, and it would build up some water pressure in this crack, which may further increase these crack widths. And if there would be some aftershock there, it would then, let me say, be more critical, and there could be some failure. So it is I would say it's a good idea to cover the cracks, especially here, because there was a heavy rain was arriving after the earthquake. So it's, I must say, good idea to show that. Now, what can be taken by earthquakes? This is also a photo I like to show. This is from Albania. It is based in the Mediterranean Sea. It is the opposite of Italy, we could say, the east, on the side of Greece. And Armenia, you may not know it. Albania, you may not know it. Is the country with the somebody has done this statistic, with the largest number of dams per capita. Okay, they have plenty of dams there. Anyway, here, but they have also some which are not well built during this cultural, what shall I say, turmoil in Albania. Once it was linked to the Soviet Union, and it was linked during the Cultural Revolution to China, and then it became have their own type of socialism and so on. So they built dams, and they built them, I must say, not all in good quality. But we see here a small earthquake occurred, magnitude 4.1, and yeah, as you can see here, it is basically a failure. Flow. Here is the reservoir. You see sharp. This is several meters here. So it is a quite, yeah, it is surprising. Okay, water level was not very high, but as we can see, this very small earthquake, magnitude 4.1, can occur everywhere. So even in Latvia, where people thought they had no earthquakes, or in Brazil, magnitude 5, I would say, occur everywhere. So it is just a poorly built dam that under magnitude of 4.1, which is also a short duration earthquake. You have these big deformations of this dam. On the other hand, if you look in this dam in Japan, 24-meter high Rockville Dam, where I just want to show you have here behind this area, you had a rock fall with or landslide with about 67 million cubic meters. It's a lot. And from this one, about 1.5 million cubic meters entered the reservoir. And of course, the reservoir you see is not very big. So if this moved into the reservoir, it displaced the water, and the water level was rising by 2.4 meters. Okay, so we have on one hand this, it looks like in a catchment here further up, we have big landslide. This caused here a replacement of the water, so it increased the water level by 2.4 meters. So if you account for that, you have to provide adequate freeboard to absorb such rain. In addition, because this earthquake was very close, magnitude 7.2, peak land acceleration in the foundation of this dam. We see here this dam body was actually 1G. At an epicentral distance of 15 kilometers. 1G, yeah, it is up to now, I must say, is the highest acceleration measured at any dam site in a footprint within the dam body. Now, what happened here? You see the dam basically with 1G, you can see it settled about 40 centimeters. So the dam basically was undamaged. It just, due to its strong ground shaking, it was just like compacted, and it was compacted 40 centimeters. Somebody asked me before, what is the allowable deformations? It depends on the dam type. 40 centimeters is no problem. Of course, it may be a problem 40 centimeters that you have a loss of freeboard of 40 centimeters. So this may be a safety problem, but for the dam body itself, it has no effect, as you can see in this case. Okay, this is a Qipingpu Dam in China, which was affected, which was shaken heavily during the Wenchuan earthquake, and where people suspected, I have discussed that in a previous presentation, about the filling of this reservoir here has actually triggered this Wenchuan earthquake. I have discussed that already. You see here, this is not the case. Also, there are still many, let me say, seismologists, they still claim that the filling of this reservoir is responsible for triggering the Wenchuan earthquake. Okay, we see here's some intake structure, power intake. Here's some intake structure for low-level outlet. Okay, we have some cracks along, this is the concrete face Rockville Dam, and we have here cracks along a vertical joint. And the problem is basically, you know, the concrete face Rockville dams, they are basically only a waterproofing membrane made of concrete, of reinforced concrete, which is maybe 50 on the top 40 centimeters to maybe 1.3 meters thick at the base. But since it is concrete, it is also built in, let me say, in blocks or in panels, which have a width of about 15 or 16 meters, and between the panels you have these joints. And of course, if you have a water load which acts vertical to this plane, you have no problem with this concrete base. It must just be watertight. And the joints here, I mentioned already, like in gravity dams, you put water stops, and here we have special water stops have been developed for concrete face rockfill dams, because the movements in embankment dams are much larger than in concrete dams. So there are some special water stops have been designed which are capable to absorb relative movements of several centimeters. Otherwise, in concrete dams, the water stops, the movements we expect is one order of magnitude less than in the case of this concrete face rockfill dams. Okay, so anyway, what you see here with spalling of concrete, it shows that here now large stresses developed within the plane of these slabs. Or for water load, you have no stresses here. Stress is zero. But now, due to earthquake action and due to the different deformational behavior of the rockfill and of the concrete face typically has a modulus of elasticity of, let me say, on the seismic action. Here it could be 30, 35, or even 40 gigapascal for the concrete. And the rockfill itself is, I would say, it has a modulus of elasticity of less than 100 megapascal. That means a factor of 300 in stiffness difference. So the deformations will be quite different. So if you have large deformations in the rockfill, some deformations, it will create very high strains and very high stresses in the concrete phase, which then cause this spalling of concrete, where the compressive strength or shear strength of the concrete of about 30 megapascal is already exceeded. Okay, we see here we have some horizontal joints, and we have, due to the settlement deformations of the rockfill, there have been some offset, and we have over some shear movement here. Okay, that is with the concrete phase. Now, if you look in the concrete dams, I've also shown that. I would like to mention if you have some ground displacement, because this pier here was built on a fault which moved about 9 meters vertically and to some meters horizontally also. It is clear that a concrete structure cannot be built safely or cannot be designed across a fault which will undergo movements of several meters as shown in this case. Now to the Cepheid roof dam once here, I would just like to draw your attention. I think this dam is up to now concrete dam which has experienced the highest earthquake action. It was damaged here in the top portion, and therefore it was decided just after the earthquake to lower the reservoir, and for that purpose, you see here these so-called irrigation outlets, because one of the main purposes of the reservoir is irrigation the rice fields here in Iran downstream. So Iranian rice comes from this area. So we see here the bottom outlets or low-level outlets in operation just after the earthquake. Okay. And it shows in order to lower the reservoir, to have such devices is actually very useful. We have here these cracks which developed in the buttress. Upstream phase, you have some cracks mainly developing in concrete times, you have to say, is also repetition. Cracks develop basically along licked joints, cold joints, you can say. They have not been cleaned perfectly, so we so the strength properties here at this joint are different, are smaller than those in the surrounding concrete. Okay, has been strengthened and has been repaired by rock anchors as shown here. Pertinent structures and equipment. Okay, this is again a safety route. There are in all power plants, you know it in India, you have colonies, I think is the name. And here, I don't know how they call it in Iran, but they also have a number of buildings, people living here upstream in villages, but they are not designed for the same seismic effects as the dam. And you see here, during that Manchil earthquake, these buildings basically were all destroyed. When we were there, we were just put into a ship container. We have a power plant here, which is a control room, also damaged. You see the switch yard also damaged with the insulators. And would like to mention, just qualitatively to look at it, these insulators here are characterized by high center of gravity. Okay, the ground shaking, high center of gravity. So we have a large overturning hazard. In addition, the switch yards in the mountainous regions are partly on excavated material and or on excavation, and partly on fill material. And if you look into seismic codes, buildings in India, for example, not only in India, everywhere, fill is actually the poorest soil condition which exists for in the soil classification. So you have some deformations. So the equipment built on the fill part is most vulnerable to seismic action. Again, the rockfall, there are some structures which are very vulnerable to a rockfall. It just needs 2-3 cubic meters of block, basically, to overturn this transmission tower. So therefore, in mountainous region, you have to assume if you do not provide special protection, which is missing here, that power supply will fail during a strong earthquake, and that means your power plant will be shut down. This is from a bench one, from a rockfall. Rockfall can be quite intensive, as we see here in this powerhouse. We have just the infill wall. Infill wall usually is some unreinforced material, and the stones falling from greater height and hitting this infill wall at high velocity, it creates, you see, it creates holes like somebody was shooting at this building, but it's just from rockfall. Okay, that were from a natural environment. Now let me come to the man-made hazards in the AM project and protective measures. Again, here the man-made hazards are basically design errors. They are hidden, you do not really know. Okay, and poor construction. It is man-made faulty operation of equipment or inadequate rule curves or reservoir operation under extreme conditions, for example. We have sabotage, terrorism, and acts of war, and we have other hazards or unknown hazards. So therefore, the protective measures depend on the unknown hazards, and we would say now Okay, cyber criminality is a hazard, is a new hazard, unknown hazard, and but it has to be looked at quickly. Where we are involved in a new dam project in Laos at the Mekong River. Luang Prabang is the name. It is 20, 30 kilometers upstream of this former capital, Luang Prabang. And there, basically, people have to look now into the cyber criminality hazard that that somebody opened suddenly all gates automatically, so it would create a floodway corresponding to, let me say, a PMS. And then it may cause a large PMS, of course, will cause quite substantial damage. So this load case is already emerging. It is not just climate change. Now, okay, this is faulty operation. Also in the US is a pump storage plant. This is the upper reservoir here. And the problem was, I have also shown it before, was that people were pumping water in the upper reservoir, not knowing that the reservoir was full because the water gate was not functioning properly. So the operator was not knowing that he was pumping and pumping. And when you pump too much, it overtops, and you see it overtop, it destroys this concrete phase rock dam, even that on the geotextile membranes because of leakage. So by inadequate operation, you can cause failure of the dam. I show here. What is the design error here? If I make all of this dam, is there has been no spillway because the engineer thought it is on top of a hill, so there is no inflow. It is logical, but he forgot to think somebody is pumping 100 cubic meters per second or so, and then it will overtop and it fails. So even if you are on top of a hill with no inflow, this is a part of pump storage, you must have a spillway. Okay, this is that simple. Okay, we see here some parts of its concrete face. Rockfill dam doesn't really look like what you say rockfill, but from the compaction and so on, it looks more like earth. Okay, the other one is we worked quite a bit in Albania. People were concerned with also concrete face rockfill dams. It was designed at that time just after the Cultural Revolution in China by Chinese, because they had close cooperation with China. And since the dam was made basically of gravity material, they also have a surface protection here. Yeah, does it come the point? Sometimes the pointer doesn't want to go here. So the surface protection in the downstream area is also a concrete slab, which protects the gravel fill material from erosion, you see here. But from the operation of the spillway, there are two tunnel spillways of this side. It creates a big eddy here, vortex, which, with relatively high velocity, which causes here erosion, you see, of the dam toe. So people were very much concerned about that, but the dam is very thick. Erosion here doesn't play a role on the dam safety, but in the newspapers they were writing that because this will not be a failure mode of the dam. So we have done some tests here, hydraulic model tests also about the ultimate depth of its scour hole and how much it could extend. Let me say this erosion is also close by the powerhouse, maybe 200 meters away, which could be affected by this, let me say, scour hole. The other man-made effect, so it is the operation of a spillway there which created this kind of damage, which I've just shown in Albania. This is from the Philippines. Okay, is a warm country, tropical country, high humidity, which we think. So what grows here in half a year, it takes 20 years in Switzerland to grow. We see here with Tranian, with radial gate, is a lot of growth. This growth is bad. It must be removed because it accelerates here the deterioration, basically, for the lifespan of this structure. Also, we see here is some rust here. This is also the gate here. We see some rusty places. Okay, this is already more than time. If you see this rust, that people should review the corrosion protection. Otherwise, the lifespan will decrease very rapidly. As you know, the corrosion process is not just a linear process with time, but it will grow basically exponentially with time. So here, I would say, if you want to have to save the money, you have to provide proper maintenance. You see here is again from Albania. We did quite some studies there. You see this spillway gates is a maintenance issue. We have some leakage. Okay, the reservoirs were full, so or were quite large, so people did not really lack water, but it is not, well, what shall I say? It doesn't look good, and people have some doubts about the safety of these spillway gates if they see this big type of leakage. Also, the penstock here to the powerhouse is the same project. You see here some parts are heavily rusted, so we could say it is not well maintained. And these countries are poor countries. I would say they should be interested to extend their lifespan as much as possible, so they should provide this proper maintenance because the saving would be very substantial. This is the Attapulgite Rockfall Dam I mentioned already. We talk here about man-made hazards, and here the man-made hazard was that they built the dam too quickly. It is a construction quality issue. The dam, okay, is about 1,600 meters. It is one of the world's biggest dams, biggest project in Turkey. We were actually the designers of that dam. It looks very nice, and as you, from far away, spillway here, it looks very nice. There are, of course, here power intakes, penstocks, and the powerhouse here, 1,500 megawatt. It's also partly some foundation problem here. Some parts were with some karstic elements were also encountered in this case. But due to the rapid construction, because it was ordered by the president and then president of Turkey, it was the top portion was not constructed in a very good quality and was not compacted. So therefore, afterwards, after the inauguration, because large settlements were observed, large means meters, several meters, not only a few centimeters. So large deformations were observed, and therefore it was decided to remove the top 15 meters of the dam and to rebuild it. So it's 1,600 meters long, 50 meters. It's a couple of million cubic meters of well, it is a substantial amount of material which have been removed and which have to be replaced here. Okay. Since the dam, I would say, is undergoing some deformation. It's basically built by basalt. Basaltic rock has some problems for rockfill dams. Also, basalt, the material itself, is a very high strength, and it has modulus of elasticity, which is extremely high. But if it is built in rock-fill dams, because of the interlock, the size of the porosity and the void area, the void ratio, it is basically the modulus of elasticity of the rock fill is actually low. In some cases, it's only 30 megapascal. In Brazil, we have quite a few of them. So you have to be careful with if you feel that the high strength rock fill will give you a rock fill dam with a high modulus of elasticity. It's not enough. Not true. Okay, here something again man-made, rapid safety deterioration. This is again in Georgia, ex-Soviet Union. This is the Inguri Arch Dam, and it was the highest world's highest arch dam for quite some time. I'd like to say for those who are interested in arch dams, they provided here a so-called peripheral joint. People in Italy call that in Pulvino. This is basically an Italian invention, and it prevents this Pulvino to, and here we have below, we have what we call a concrete saddle, and by building this concrete saddle, you can achieve, well, a dam shape, which is close to symmetrical. And we know if you have an arch dam, which has basically a symmetrical shape, its seismic, its dynamic behavior is much superior to the dam, which has a highly asymmetric shape. So therefore, with this Pulvino, you can achieve a higher degree of symmetry. A disadvantage, in addition, at the dam foundation contact, you have high tensile stresses in the upstream phase of the dam, and by providing this joint, basically you eliminate these high tensile stresses, which have been a headache for some people for quite some time. Okay, anyway, it was built at the end in the 1980s, and it was only finished, let me say, a few years before independence of Georgia, and because of the 5-year plans and so on, it had to be completed in a rush, and people have not done all the necessary grouting works, have not completed that, and you see here at the low-level outlets here, we have a lot of leakage. It was about 10 cubic meters per second, which was just released because these gates here were not properly designed. So this dam had to be upgraded. I must say, when it became independent, 1989, 1990, there was also civil war in Georgia, different groups fighting against each other, people not being paid. So therefore, people on the dam side, they were looting the dam, world's highest arch dam. They were removing all copper cables. They were removing drainage pumps in low-level galleries. So therefore, also the dam was new. You know, it was designed for 100 years. Should it be there for more than 100 years? It even within, let me say, 5 years, it had to be declared as unsafe. Also, it was maybe only 10, 15 years old. So I would say if you lack maintenance control, people were no longer sure what is the behavior of a dam. It is and it is man-made. If you do not take care of a project, I would say it will become unsafe very quickly, even if it has been designed for much longer periods. So the proper maintenance is a key issue in the long lifespan dams. Now we talk here about effect of war. The British Air Force has attacked some of the German dams, some masonry dams. As you can see here, there are some nice movies on the development of these special bombs which were used there, and you could see the explosion of this one bomb. They created here a big opening here in this dam, and it caused the release of a reservoir, and it caused the loss of life of many people here in Germany. I think 3 dams were attacked, two masonry dams which were destroyed like that, and one dam was Embankment Dam, but the Embankment Dam being quite wide, it did not fail. This I've shown already for terrorism protection. Now let me say here the case, I don't know if you're familiar with that, is Sayano-Shushenskaya. It is at the Yenisei River in Siberia, in Russia. I must say I was also there about 15 years ago. And this shows this is the highest dam in the former Soviet Union or in Russia. It's a 242 meters high, is 6,400 megawatts. Okay. Big project. Now there was, you see here, construction period. It took a long time, 22 years, okay, until it was actually really finished. Okay, we see here the spillway, kind of big spillway is powerhouse here. So during this is a picture, yes, the dam, how it looks like. Powerhouse here. We were on the ice-cold mission there once. Yes, I visited that. It was quite interesting. There was nobody on the site who could speak a single word on the English. So it was really interesting. Okay, we still see here a spillway. We see here like a penstocks for the powerhouse. Okay, what happened? The dam actually is quite thick. It is, I would say, it is an arch gravity dam, but the valley is very, very wide, as you can see here. It's looking downstream from a crest. In winter, it's in Siberia. It's Yenisei River in Krasnoyarsk is the capital of, let me say, of Siberia, basically, if you can call it like that. So it goes here about 300 kilometers further downstream is Krasnoyarsk. It's a bigger river. Okay, there was an accident in 2009 here, and in this accident, actually, in a powerhouse, 9 out of 10 units were destroyed or damaged, and repair took 5 years. Do that again. Okay. Now, this power plant then was out of operation, and it is clear the Yenisei River is a big river, plenty of mosquitoes in summer. And here, then they have to release the water here to the spillway during 5 years. You know, the spillway is basically only designed for releasing water just for a few days, but not for years. So therefore, okay, this is a picture I have taken here. You see, the powerhouse looks quite nice. It's a little curved. Okay, that is when I was there in 2007, but the accident occurred in 2009. And you can see here, this is the accident. They did some repair work at some turbine, and there was a failure of some bolts, some fatigue failure due to vibration, and therefore during maintenance work, they had a failure of the cover of a turbine with a head of 240 meters, and it then destroyed powerhouse, and about, I think, 70 people were killed. Okay, we see here kind of the damage here, Unit 7. This is now a powerhouse, which I've shown before. You know, with this huge pressure, 240 meters head. Even big concrete parts here are quite heavily destroyed. even power plant. It was the damage, almost $1 billion damage. Even Putin, he comes here to have a look at this big accident because, as I said, about 75 people were killed. Okay, now what was then the problem? This problem was made during, let me say, electromechanical work, and due to the failure of both, it has not affected the dam, the accident for the powerhouse. So it would be not a problem for dam safety, but eventually it also becomes a dam safety problem. I must say, it basically took with people also about 2.5 hours to close the gates here to the power units and also to open the gates of the spillway. Because the automatic opening did not work. But as I said, it had then to be operated during years. And in Krasnodar here, at this Yana Sushetskaya, the temperatures dropped quite low. It is -40, exceptionally, they could even have -50 degrees. So therefore, if you operate the spillway, and you see here the big cloud here from the operation, it creates ice. So you see a spillway operation. This is now in a colder weather. Okay, so some equipment here, everything under thick ice. So quick through that. This is a spillway. This is a bridge here with a crane bridge. We open also some gates. And it created here ice blocks. Yeah, they are already 20 meters high. They're not small ice. So therefore, people were suddenly concerned if this bridge here, which is for a crane here, if it actually can carry this big loads here. Okay, it's not a dam safety issue in that. So people have removed, okay, these tens of meters of ice created by the operation of a spillway. We see here, this is you could not do anything, so you have to operate the spillway. Okay, so these are man-made. It does not really create problems to the dam, only when they could not open the spillway gates. So therefore, if the water would flow in, eventually it could have overtopped that. Now, the other one, the last one I would like to mention is structural or project-specific hazards in dam projects. Structural hazards could be a blockage of spillway gates due to floating debris. Okay, that depends on the type of gate or lack of maintenance. Okay, there are different failure modes of spillway. Some are man-made, but some are due to the type of design, So therefore, we call it structural hazards. And we could also have some differential movement of structures along joints or interfaces in concrete structures and embankment dams and so on, or also block joints in concrete structures. And in a case of embankment dam, we can have piping or seepage, and depending on type, dams, we can have foundation seepage due to damaged ground curtain or dissolution of minerals. You can have electromechanical failure and so on, aging, alkali aggregate reactions, so which I would say are project specific, but they may overlap also with the other hazards which I have mentioned before to some extent. This shows one in Switzerland, built about 75 years ago. At that time, people used very high water cement ratio because for placing this concrete, they didn't have vibrators at that time, so it was a high water cement ratio. And if you have high water cement ratio, the permeability is high. We only have dense concrete. we cannot have a high water cement ratio. And here also the concrete becomes vulnerable to low temperature, so therefore the surface of this dam is covered by granite blocks, about 50 centimeters deep. So therefore, to protect, inside is all concrete. Only outside are these granite blocks. They are there for frost protection. So I should come to an end. Here is a Mosul dam. Maybe you have heard about that in Iraq. Actually, we were also the engineers of this dam. It was considered the most dangerous dam in the world. We are not proud of that, you know. But I just want to say why we have this problem. It is about 110 or 120 meters high. It is just in Mosul at the Euphrates River, and it is a massive dam, and it was built completed in the 1980s, even during the time of the war with Iran. Okay, now Mosul Dam, the problem is that in the foundation rock, this is just a simplistic view, there's gypsum anhydride, and if the reservoir is built, you have a seepage in the foundation, and the water seeping through the foundation dissolves the gypsum, and as a function of time, it will create cavities. So therefore, people knew that at the time of the construction, and it was still decided that this time has to be built. So therefore, a system was introduced where people were grouting here in this dam 10 days a week, or let's say 24 hours and 365 days a year. So people were grouting continuously, basically to find out an equilibrium between the dissolved material and to replace that by grouting. So many thousands of cubic meters of grouts were here injected every year. So this is already problematic. It became more problematic, I think, in 2015 or 16, when IS, okay, this Islamic State people took over this dam and they destroyed the state equipment. So therefore, this kind of routing equilibrium, which would allow to have a steady state safety, they destroyed that. So this operation was disrupted, and which basically caused the increasing risk, that increasing cavities. And if you have cavities, you may have eventually sinkholes if they fail, so they could affect the dam. Okay, after a few weeks, the Americans, with the help of the Americans, they could reconquer the dam, and they started with a project basically to rehabilitate the overall system, so we can have this kind of problems. Okay, this is the case of the Mosul Dam. Now, I must say the situation is again stabilized, and the dam is a well-built dam. It is a weaknesses in the foundation, and at this time, everything is under control, and the dam is safe. So there is no need to declare it as the most what's the most dangerous dam in the world, as somebody has claimed. I mean, probably it was at that time, because volume is quite large. If it would fail, probably 500,000 people would be killed if it would fail. Okay, this is again in Ethiopia. It shows it is in a basaltic rock here, or volcanic rock formations with different layers. So therefore, this rock is highly fractured, and they have a problem. You can see it. This is at the the reservoir level is not even very high. That at the downstream toe, here we have a lot of seeping water, and people came up with plenty of camels to feed it. Okay, the other type is project-specific one is the San Fernando dam, because it was built on hydraulic fill material, which is susceptible to liquefaction. As we can see here, the large deformations which occurred during the 1971 San Fernando earthquake 50 years ago. Okay, we see here this rupture. The dam did not fail because the water level was relatively low at the time of the earthquake. We see here the access to the intake tower. The access bridge also damaged during this strong earthquake. Okay, it's quite a big community living downstream here. So after the earthquake, the freeboard, I think it was about 1.5 or 2 meters. Okay, what I've showed you at the beginning is the Tom Sook concrete face rockfill dam. It eventually, the one which I've shown, it was replaced by an RCC gravity dam. And this RCC gravity dam, of course, is not vulnerable to overtopping. Okay, that is it. One. The other one I would like to mention is here. This is also from a Wenchuan earthquake, which is an intake structure, intake tower with on top you have a gate room structure here where you have the equipment for lifting the equipment for the gates. And here we have this problem. I like to show that after that earthquake, the reservoir level, as you can see here, was quite low at the time of the earthquake. The reservoir was low here. It's basically it's not dangerous. We could see, but during the earthquake, there was some control board, as we can see here, which were just outside of a building, which even overtopped. And you see quite a few Chinese engineers and so on standing around trying to repair these things, because the safety started to deteriorate, because after that earthquake there was heavy rainfall and the reservoir was starting to being filled again. And it is clear, if you cannot control the reservoir level after the earthquake, the dam has been damaged, and you cannot lower the reservoir, basically it would be eventually, would be overtopped, and the gates could not be operated because the control units here failed. So basically, due to this small, what shall I say, incident, where some electromechanical engineers did not do a proper work, or the specifications were not accordingly. Due to the failure of this control board, it was not possible to operate the gates. And this dam, from day to day, it is a little exaggerated. It's exaggerated when I explain it like that. It became unsafe. Just weeks after, or a few days after the earthquake, this dam, which was basically almost empty, it became unsafe because people were not able to open the spillway gates. Okay, now to come to the conclusion, the time is also up there. We can say large dam projects may be subjected to a large number of hazards, which have to be considered in the design, during construction and operation stages, and in emergency action plans. Okay, so it is quite important. Some people feel we have to do special safety measures only for the earthquake hazard, but I must say this is a little one-sided, because if we look at the overall safety of a plan, we have to address basically all possible hazards. Now, the hazards which we have to consider are natural hazards. I mentioned them, man-made hazards. I would say they are probably the most difficult to deal with. We cannot predict some of them. For the natural, it is just the seismic hazard, which I feel is very difficult. We have site-specific hazards, topography, and so on. Most of them have shown the properties of the foundation rock, prone to dissolution, and we have project-specific hazards, to which depends if you have a gravity dam or a concrete dam, or if you have embankment dams. So these hazards will be different. Now, number three, new hazards are mainly man-made hazards and are a result of the technological progress. These developments may be used by terrorists, saboteurs, and criminals. I mentioned cyber criminality. Okay, to these days, let me say, it is apparently easy to deal with drones. You know, just remote by some terrorists, they can attack some vulnerable parts of some power plants by drones. Most hazards are time dependent, including climate change. Like to say, at this time it seems that only climate change is time dependent. Now, this is simply not true. It is most hazards basically we have we have to consider are time dependent because, for example, safety standards are increased as a function of that. So the protection against these hazards also increased. Now, by periodic, I would say what is very important, and please don't forget that by periodic safety reviews, which I mentioned at the beginning, the time development of all the hazards, including the much discussed climate change hazard, can be accounted for. And this has been standard practice in the dam industry for a long time already. So I must say, for dam safety, the effect of climate change on dam safety, I'm not very concerned because the mechanisms are here, how we can deal with these safety concerns. Okay, with that, it's just time. I would like to stop, and there is time for a few questions. If somebody has some questions.
Yes, Mr. Ashwini Kumar, you may ask.
Yes, sir. Good evening, sir. Sir, I wanted to ask about, we had a situation in Tom Sook where there was a failure. That was basically a pump storage project, wherein we had a reservoir, an upper reservoir and an existing lower reservoir that was very large. So we also, in India, there are a number of projects coming up in such a manner, but many a times the project proponents propose uh, uh, penstocks very close to the upper reservoir. I mean, just below the embankment in the upper reservoir, they tend to allow penstocks to pass below that. So, are they? There's a possibility, of course, of transfer of strong vibrations from the penstock to the dam body. So in that case, do you think it's a hazard to the dam body? And second, are there any guidelines for that?
Well, I would say, okay, I don't know how it's a construction, but with a penstock, it would be a concrete structures. You know, the hazard I would mainly see if you would have some ducts going through an embankment dams. This is a kind of a problem because you would have seepage could develop along the interface of concrete or of your pipe and the embankment material. But I think this will not be the case for a pump storage plant, and I think it is okay. Also, the vibrations, I think the vibration levels will be small. I don't think we have done quite a few measurements on operating of some plants, you know, for frequency control of the grid, and I must say the problem there is not for the dam body, but we found it was more a problem for fatigue in the steel penstock at supports where you have stress concentration.
All right.
So you could have such kind of problems. But for the concrete, I would say I would not be concerned much.
So a major concern was if from the penstock, let's say they are underground, they're passing through the rock, let's say 5 to 10 meters below the embankment in a sound rock. So due to the vibration transferred to the dam body, made out of any fill material, there could be possibility of liquefaction. Do you think?
Yeah, yeah, but when I think today we do not build dams at the locations with liquefaction. So if you have liquefaction, you will need very high, let me say, vibration levels, and the vibration levels due to the pressure fluctuation in a penstock are small ones.
All right.
I would say the displacement or acceleration, if you would record them, they will be very small. So I would, they will not cause liquefaction.
All right,
I
sir.
would say this is not an issue. But if you would have liquefaction, then this material should be removed because during a strong earthquake, it would then liquefy, not due to the operation.
Fine, sir. And sir, uh, last time when we were discussing about this case study of Tom Sook in US, you were talking about having an bottom outlet for emergency situations. To have an bottom outlet with enough discharge capacity. So, what is the criteria of having what amount of discharge capacity should the bottom outlet have?
Uh,
When the,
okay,
let's
okay,
say,
there are some. Okay, so a rule of thumb in Switzerland we say the discharge capacity of a bottom outlet is such that you can lower one third of a reservoir within 8 days.
so it is.
Yeah, but this is for small reservoirs. If you have huge reservoirs, you cannot do it. So you have to extend this period. But as for the smaller reservoirs, we say 8 days.
All right, but that situation, can that be avoided? Like in Tom Sook, due to mismanagement or the faulty due to a faulty instrument, they the input the water inlet could not be controlled. Hence, even if they had a bottom outlet of lesser discharge, they couldn't do anything. They probably would have faced an overtopping. So, how can we prevent, or what measures can we take right now in our designs for?
Well, I would say in the pump storage, I would say maybe the bottom outlet you do not need because you can lower the reservoir basically, yeah, by the power plant, but it would still be useful. But for overtopping, you would just provide a spillway. If you pump 100 cubic meters per second is the capacity of your pumping system, you design your spillway maybe for 110 cubic meters per second. You know.
Okay, that could be a way, but
But the bottom outlet, okay, yes, you can still do the bottom outlet if the power plant would be out of operation and you could not lower the reservoir due to, let me say, through the spill, through a powerhouse.
so most of the project proponents do not propose what you call spillways. They only have a continuous loop of embankment dam for the other upper reservoir. So, uh, and they don't consider that thing that in case the pumping is continued for a longer duration than intended, uh, for that, they, how do I'm not able to, I mean, decide upon how can we prevent that.
Well, to prevent, I think once it needs a human intervention and somebody can make it wrong. So I would say if you provide this spillway, then you do not have to be worried about this failure mode. So you just, in Switzerland, we also built some new pump storage and we are doing some in the Philippines and so on, or it's just on a drafting in a design stage. But it is clear that you do a spillway there. Also, you have no inflow.
All right.
But some people feel they have invented. I think once somebody explained in Germany, they thought they have their own system, which makes it impossible that they have overtopping. Okay, I don't know exactly how it works, but with the spillway, it is straightforward. Just an ungated spillway, just an overflow, you know. It's very simple.
All right, sir. That should do. Thank you, sir. Thank you so much.
Are there any other comments or questions?
Do we have any more questions?
If it is not the case, basically you can also send me some emails if later on you feel you have some questions. In this case, I think we can close this today's presentations.
Yes, sir. I guess we don't have any more questions. We should conclude the session for the day. See you all tomorrow at 1100 hours.
Yes.
Thank you for the day.
Okay, yeah, welcome. Okay.
Thank
Good
you.
evening.
Take care.
Thank you very much. It was very interesting.
Yes, please.
Yes.
Do we have the questions? No.